Okay. Hello, everyone. Welcome to our faculty candidate talk. And today we're really glad to have Professor Xiao Liu from University of Arkansas visit us and give a talk on domain-aware statistical learning and its applications. So Professor Liu is the John Imhoff Endowed Chair and Assistant Professor in the Department of Industrial Engineering. And before that, he is a research staff member at IBM Thomas J Research Center. And his research mainly focuses on the domain-aware, data-driven methodology for scientific and engineering applications, environment and energy, urban resilience, applied statistics, system informatics, and reliability engineering. And Dr. Liu's work has been recognized for different societies, and he has received several distinguished awards, including the National Science Foundation Career Awards, and his research has also been supported by a variety of agencies, including NASA and industry. And currently, he also serves as the president of Data Analytics and Information System Division of IIC. So, very impressive. Thank you.
Thank you so much for the introduction. And it's such a great pleasure for me to be able to come here and take this opportunity to share with you my research. In the following about 47 minutes, I will provide you a complete picture of what I have done and what I plan to pursue in the future. So this is the agenda for today's presentation. I'm going to start with some background and introduction to myself so that you will have a better understanding of why I'm working on these problems. And then I will spend some time on a statistical learning framework for advection diffusion type of processes and talk about its applications in multiple domains. And after that, I will discuss some extensions on the statistical learning for general nonlinear dynamical systems. And finally, I will present you a roadmap that summarizes my past and future research. As you will see that there are lots of exciting problems that I would like to share with you, but given the time that I have, I will have to maintain the depth and breadth of my seminar. So here we go. So I have background in both mechanical engineering and industrial and systems engineering, and perhaps this partially explains why I'm interested in the integration of engineering domain knowledge and data-driven approaches. When I take a look at the past 10 years, there are two research experiences that really significantly shaped my current trajectory. From 2012 to 17, I was a research staff member at the IBM Thomas J Research Center. I spent the first 3 years in Singapore on a research project there, and then the last 2 years in New York. After that, in 2017, I joined my current department. So when I think about these two experiences, the first experience really enabled me to identify my passion and what I plan to do in the next couple of years, and the second experience allowed me to experiment on many of my ideas and establish the foundation for my future career, as you will soon see. After I joined IBM, the very first project that I was involved was a research project funded by the Singapore government on urban environment and sustainability issues. So over that 3 years, I worked on different problems such as the modeling of urban pollution processes, tropical extreme weather events, and the wildfire smoke propagation problems. So if you look at these processes, one thing that they share in common is that these are natural processes governed by the laws of nature. So we have not only massive data sets collected from these processes, but fairly strong engineering knowledge or physical knowledge about them. For example, many of these processes are spatial temporal processes whose dynamics can be governed by advection diffusion equations given in the form of partial differential equations. For example, Xi here is the quantity of interest, and A here is the advection diffusion operator that often depends on the parameters of the physical process, and Q is the external forcing term, which is the source and sink term in this application, and epsilon captures the uncertainty. And of course, a real physical process can be way more complicated that cannot possibly be captured by a single equation, but this is perhaps the most important equation that captures the fundamental dynamics behind many of these processes. So to model such processes, physics-based approaches have been widely investigated, and which typically involve solving these partial differential equations using numerical solvers. And these approaches, they have advantages in control, design, and planning, and what-if analysis. For example, what if there would be a new factory on the east side of Madison? How that factory will affect the air quality of the city over the next 5 to 10 years? We could probably run a physics model to answer questions like this before we even have any observation data. And of course, running a physics model is not always simple. For example, it's hard for us to make real-time predictions. If you think about the computational complexity associated with solving those partial differential equations, it's not that straightforward for us to incorporate sensor observations, especially streaming data in real time, which happens to be one of the most important input data type in the age of IoT or big data. And many of these physics models may not perform very well for short-term predictions given the input and modeling uncertainties. For example, if I want to know whether it's going to snow after 15 minutes, perhaps I don't need to run a physics-based model. The best practice is just to step outside, take a look at the sky, and I can draw my conclusion based on my observations. And for this reason, statistical spatial temporal models have also been widely investigated, which typically involve constructing some random processes with some space-time covariance structure. And the advantages of these statistical approaches are clear. They enable us to incorporate observations, scientifically quantify uncertainty, and many of them perform reasonably well for short-term predictions that supports real-time operations. And of course, for a complicated physical process, constructing these statistical model, again, is not going to be easy. If you think about the space-time covariance structure, most likely it's going to be non-stationary and isotropic, meaning that it could be different over time. It could be different along different directions if you think about the change of wind speed and wind direction. And it may depend on the parameters of the physical process or the boundary conditions of the partial differential equation. So in that case, it's very difficult for us to specify or sometimes even envision how the space-time covariance structure should look like. If we're not able to connect the data-driven model to the domain knowledge, and later on we may run into some trouble when we try to interpret the model, when we try to let the model generate some actionable insights for us. I remember during my days with IBM, we had these weekly meetings with different domain experts, for example, environmental scientists. And one pretty painful lesson that I learned was how difficult for us to convince them to adopt our model if we're not able to justify our model using their domain language. So there exist both theoretical interests and practical needs for us to explore the convergence or integration of governing physics, engineering domain knowledge into data-driven approaches, such that we can leverage the advantages of both physics-based models and data-driven approaches. And we believe this is particularly important for ISE because we're dealing with high-stakes applications that often require interpretable models, explainable decisions, and actionable insights that facilitate the discovery of new engineering knowledge. This is like the overall goal of my entire research and the main objective of my current NSF career proposal, which is to pursue interpretable, domain-aware, data-driven models that facilitate actionable insights. So if we look at the literature, there are a few existing strategies that enable us to do so. For example, we can incorporate domain knowledge as space impliers. This is a very natural way for achieving this goal. Regularizations or different kinds of constraints. For example, we have seen researchers impose boundary conditions to the covariance structure of the Gaussian process. We could approximate a physical process using data-driven models, such as using statistical surrogate models or emulators, for example. And then we can use data-driven approaches as a bias correction mechanism to correct the systematic bias associated with many physics-based models. Or, of course, we can use powerful tools such as the physics-informed neural network or physics-informed kriging, and, of course, explainable machine learning, which typically involves constructing a secondary model in order to explain the primary model. So all these approaches are powerful and very useful given different problems at hand. So in our research, we developed a new modeling framework that enables us to integrate advection diffusion equation into data-driven approaches so that we can further advance the state of the art. So let me come back to the advection diffusion equation. So this is the equation that you've already seen, which can be widely found from a spectrum of engineering and scientific applications. So cosine here is the quantity of interest. To model data arising from such a process, we could use spectral decomposition or eigenfunctions expansions to decompose this spatial temporal physical process into two components, a spatial component and a temporal component. So the first component, the spatial component phi, consists of a set of basis functions that span a spectral space. For example, we can use the Fourier basis, or we can learn the optimal basis from data using tools such as proper orthogonal decomposition. So I'm going to talk about both approaches in this presentation. And the second term, alpha, can be seen as a multivariate stochastic process in time whose dynamics can be captured by some stochastic differential equation, which is usually not known. So G here defines the dynamics of alpha. So as an illustration, suppose that we're dealing with a weather system. So what you're looking at here is a sequence of Doppler radar images of a precipitation process. So if we use the Fourier basis, we can actually see how the obtain the dynamics of alpha. So this animation shows how the elements of alpha evolve over time, both the real part and the imaginary part. And again here, alpha is a vector and whose dimension actually depends on the dimension of our data, in this case, the image. For illustrative purposes, let's just focus on the top three elements of alpha, which correspond to the lowest three frequencies. We could actually see how these top three elements of alpha evolve over time. That's what you can see from the animation on top. And of course, when we deal with a nonlinear system, so the elements of alpha are all coupled in a sense that they're going to co-evolve together and forming this interesting trajectory of the system projected onto a three-dimensional, low-dimensional space. So this observation really suggests that sometimes instead of directly modeling a pretty complicated spatial temporal physical process in the physical domain, we could instead focus on modeling the dynamics of alpha. Because although the original process seems to be pretty complicated, the dynamics of alpha clearly presents some pattern that can be captured by data-driven approaches. So if we're going to follow this approach, then the next question is, how do we determine the dynamics of alpha? In other words, the structure of G. So now we have two options. The first option is to use pure data-driven approaches to learn the dynamics of alpha. This is possible. We could start with some parametric assumptions, structures, and then we can use data to estimate those unknown parameters. Or we can use some existing approaches to identify the PDE that governs the dynamics of alpha. So, or alternatively, we could go back to the original advection diffusion equation and perform further investigations on the solution structure of this advection diffusion equation to see if the physics equation can tell us something about the structure of alpha. And of course, this is not always possible given any arbitrary PDE, but once it is possible, the dynamics of alpha or the structure of G will be completely determined by the governing physics. In that case, we can make a fairly strong claim that because we're dealing with data arising from such a process, then the dynamics of alpha must have certain structures which greatly help us justify our modeling choices. And this framework can potentially bring us a few key advantages. For example, because the basis functions are fixed, whether it's pre-specified or learned from data, the modeling of the spatial temporal physical process can be converted to the modeling of a multivariate stochastic process in time, as you've already seen that the latter problem is often more mathematically tractable. And if we're able to derive the dynamics of alpha from the governing equation, we could naturally or intrusively embed the governing physics into the data-driven model as opposed to adding domain knowledge as additional regularizations or constraints. And once the dynamics of alpha has been established, it is possible for us to find a physically meaningful space-time covariance structure for the original space-time physical process because we know the relationship between the spatial temporal process and the temporal process alpha. And dimension reduction is always possible if we only keep the low frequency terms. And of course, if we drop the high frequency terms, we're going to inevitably introduce additional errors into the model. We're going to create some artifacts in the model output, such as the Gibbs phenomenon, if we use the Fourier basis. But those issues can be well managed. If I have some time, I'll be happy to talk about that. And finally, we can embed this idea into a well-established statistical modeling framework for spatial-temporal data known as the hierarchical dynamical spatial-temporal model, which can be conceptually expressed in this way. It's a dynamic model, so the first line is based on the spectral decomposition. So if necessary, we could incorporate the bias correction term to it, as what we did in our paper. We can introduce the noise component to it in order to complete the construction of a statistical model. And the second line here captures the dynamics of alpha, which is determined, or at least partially determined, by the governing physics. So if we want to gather to build a model like this, now we have to answer a few key research questions. So the first question is, what's the dynamics of alpha anyway? In other words, the parametric structure of G given a governing physical equation. This is like the key question before we can construct this model. And the second question is, what is the physically meaningful space-time covariance structure for the original physical process, because we're constructing a statistical model here. And after that, how do we integrate the results into the dynamic modeling framework and perform statistical inference in a computationally efficient manner? So the answers to the top three questions are provided in our recent papers, and the first one has already been published, and the answers to the fourth question is provided in one of our working papers. And given the time that I have, I don't think I can dive into those details and proofs, but at least what I can do is to walk you through some of the key results reported in our paper. For example, proposition 1 of our paper presents the dynamics of alpha, which is obtained from the governing advection diffusion equation, as you can see here. So one comment that I can make here is that for nonlinear system, the components of this vector alpha, they're all coupled, meaning that this diagonal matrix G is not a this matrix G is not a diagonal matrix. It's a pretty dense matrix that depends on the physical parameters, and it could evolve over time. So it is computationally expensive sometimes for us to evaluate this matrix G. But this phenomenon can be justified as the nonlinear energy redistribution or transfer between multiple scales from the perspective of physics. And proposition 2 of our paper establishes the connection between the proposed approach and Gaussian process-based models. In particular, it enables us to obtain the covariance structure of the physical process. If you take a look at this covariance structure, it's non-stationary and isotropic because it depends on the physical parameters that change along different directions, that change over time. It's space-time non-separable. So this is the kind of covariance structure that can hardly be directly specified or validated. So, but following this approach, we could sort of let the physics tell us what the appropriate structure should look like. Again, help us justify, our modeling choices. And proposition 4 of the paper presents a stochastic integral difference equation representation of this model, which again enable us to establish the connection between the proposed approach and a large body of literature out there. And based on this representation, as you can see here, the future value of this physical process is given by its current value through a convolution kernel. But this time, this convolution kernel is derived from the governing physics. It depends on the parameters of the physical model, so therefore it's physically meaningful. So these results really enable us to switch and jump between different modeling representations so as to leverage the advantages provided by different modeling representations. Whether we're going to use this dynamic model, the Gaussian process-based model, or the IDE representation, we're going to have a physically meaningful covariance structure, we're going to have a physically meaningful kernel function obtained from the governing equation. And finally, we apply this modeling framework to precipitation nowcasting using data collected from nearly 200 thunderstorms, and we compare the performance of our approach to other existing data-driven approaches. What we can see here is that both accuracy and interpretability can be simultaneously improved by integrating governing physics into data-driven approaches. We don't necessarily have to, sacrifice accuracy in exchange for simplicity or better model interpretability, which is important for physical and engineering processes governed by the laws of engineering. So as a quick summary, so in this research, we developed this framework that enables us to integrate advection diffusion type of equations into data-driven approaches, which can be applied to many environmental processes in engineering systems where we can find lots of examples of advection diffusion processes. So now the question is, what's next? So currently, we're working on some major extensions of this modeling framework for some other exciting applications. For example, we're working with the National Renewable Energy Lab on an wildfire aerosol propagation model using remote sensing data. And why this is important? Because wildfires have significant and negative impact on solar energy production. So wildfires generate atmospheric aerosols that block the incoming solar radiation, and the particular matters, especially PM 2.5, on the solar panel surface can significantly reduce the transmittance to PVs. And this figure clearly shows the relationship between solar power generation and PM 2.5 concentration in the air in California. You can clearly see that there's a significant drop of the power generation when the fire starts. In fact, although the installed solar energy capacity in California was increased by 5.3% from September 2019 to June 2020, and solar power generation in the first 2 weeks of September 2020 was actually 13.4% lower. And that was not because we didn't have the capacity, it was because there was a major fire during that period of time. So this really shows where a potential bottleneck is. So many states like California have this zero carbon electricity target, but unfortunately the current projection shows that we're only going to have more wildfires in the next 10 or even 20 years. So making it timely and important for us to investigate the short-term and long-term effect of wildfires on solar energy, on renewable target. So currently we're at the stage working with NREL on developing this aerosol propagation model using data from multiple geostationary satellites. And this research is faced with a very interesting challenge. So if you look at these two animations, these are the observed aerosol optical depth from two different satellites over the same spatial domain over the same period of time. In other words, these are independent observations from two sources of the same underlying physical process. So we expect the results to be at least similar, but they're not at all, right? If you look at these two data streams, they have different missing rates, obviously, different, potentially different bias and errors, and even the readings can be quite different. If you just look at the circled area, it looks like the satellite on the left side even failed to see the fire down there. So that's the reason why we're currently extending this modeling framework such that it can handle multiple heterogeneous data streams, which enable us to estimate the underlying physical process, which is not accurately or directly monitored. So we have a paper in the area, and we presented this paper at Informed Conference in 2021. So the completion of this work will eventually enable us to have a better understanding of what's going on in the air, but our long-term goal is really to relate what's going on in the atmosphere to what's going to happen on the ground by answering a fundamental question that exactly how much solar energy can be generated during wildfire events, given the current and future capacity. So we believe the answer to this question will enable us and motivate us to rethink many of the planning and operational challenges during wildfire events. Of course, we need the domain knowledge from the national labs, and this will also create lots of collaboration opportunities for people from different domains. And talking about wildfires, we're also working with Argonne on developing this convolutional non-homogeneous Poisson process model for predict wildfire risks on different segments of power transmission lines. And of course, I guess I don't have time to go into the details, but if you're interested in this work, I'll be happy to have more discussions with you in the following meetings. Okay, so far I've talked about this statistical knowing framework for integrating advection diffusion type of equations into data-driven models. So In fact, there are lots of exciting research can be done on top of this framework, and that will keep me busy for another 5 to 10 years. For example, we can work on the inverse models. Currently, we're working with IBM on the source detection problem using spatially sparse observations from a sensor network. And we could also work on the process monitoring and anomaly detection problems, such as the detection of the overheated and overcooled area in the temperature field of a running data center, because these are the areas that consume tremendous amounts of energy and they need to be avoided. And recently, I've also started working with IBM on the deployment of mobile sensors, such as the planning of the mobile sensors in a data center to monitor the temperature and humidity, and also the planning of drones equipped with sensors for detecting methane leak in an oil and gas field. So IBM is working with a company in Texas on this, and we're trying to see if we can contribute something to that research. Okay, and so far, I've been primarily focusing on the modeling of data arising from advection diffusion type of processes, and most of the applications are in the area of environment, sustainability, and energy. But in fact, we can totally make the scope of this research even broader. So in the next about 60 minutes, I will focus on some extensions on the statistical learning for general dynamical systems. And again, I'm going to start with a real motivating application. So in the recent years, FAA has identified the potential collision between aircraft and UAV, unmanned aerial vehicles, as an emergent threat to aviation safety. So in order to come up with new regulations, policies, to make new recommendations to aircraft manufacturers, we need to understand what's going to happen if a drone hits an aircraft at a different impact conditions. So we know pretty well about the bird strike, but we have much less knowledge about drone collision, because drone is much heavier and stronger, and the risk will be much higher. And this is the background why agencies like FAA is interested in this kind of research. So this is like a typical problem that can be traditionally answered by performing finite element analysis. This is a very powerful tool, but perhaps the only limitation here is that it takes time. For example, you're looking at this animations. It took us about 28 hours to just complete one simulation that lasts for about 8 milliseconds. And for the same reason, it took FAA some time to be able to evaluate only a limited number of scenarios. So the key problem here is that we definitely need something that is much faster and reasonably accurate to speed up this decision process. So before I can briefly talk about the details, I want to present this general modeling framework about how we approach this problem. And of course, we're going to need some data. But we only need data generated from FEA, for example, at a limited number of impact condition scenarios, because we cannot run FEA for a large number of collision scenarios. But once we have that data set, we're able to obtain the reduced order model to bring the dimension of the problem down significantly. And then the statistical model will be built on top of the reduced order model, which has two components. The first component establishes the relationship between parameters and external force. For example, from impact conditions to impact force, which itself is a pretty complicated spatial temporal process, physical process. And the second component captures the relationship from impact force to aircraft surface deformation, the system states. So once we have a model like this, given any new parameters or new impact conditions, we can quickly predict the collision process for that new impact conditions, so that we don't have to run this FEA analysis over and over again. At least we can be more selective. We can just focus on those important collision scenarios. So that's what this model can provide. So now let's take a look at some details. So here we consider this nonlinear structural dynamics equation as the governing physics behind this collision process. So rho is mass and u is displacement. So the second order derivative of u, that's acceleration. And the second term here is the internal stress term. And the term on the right side, that's the external force term, which is determined by the impact condition. So you can recognize that this is basically Newton's second law of motion, F equals ma. Right? And if we use the finite difference discretization, we can always obtain a large system of ordinary differential equations that can be solved by numerical solvers. So in this application example, so M is the mass matrix, and the dimension is about 2 million because it's a three-dimensional problem. So this dimension is not even considered that big for this type of application. And the second term is a nonlinear internal force term because it depends on the current aircraft surface deformation vector u. And the term on the right side, that's the external force term. In particular, we consider aircraft nose metal skin deformation under different UAV flight altitude. We consider different pitch, yaw, and roll degree right before the drone hits the aircraft at a fixed speed. And we consider 35 impact conditions, 35 different combinations of these 3 degrees generated by the Max Pro space filling design. And for each design parameter, the range goes from minus 45 degree to 45 degree. And then we can perform FEA analysis to collect our data at those from those 35 impact conditions. And this is just like one illustration that shows the deformation process at the 35th impact condition. You can clearly see where the collision happens, the propagation of stress wave, and the formation of some new deformation area at the edge of the physical domain. This is because there are 3 rivets there connecting the aircraft surface structure to other parts of the aircraft. And this figure shows the final moment, 8 milliseconds after collision, aircraft surface deformation for the 35 impact conditions. You can clearly see that different impact angle can lead to different, damage. That's the reason why we need a model to capture such a relationship. Okay. So once we have data, now we can obtain the reduced order model from the full order structural dynamics, but this time we're going to use proper orthogonal decomposition, which enable us to project optimally the long-dimensional, the high-dimensional displacement vector u to a low-dimensional space spanned by the PUD basis matrix V, which can be found using extended approaches, singular value decomposition. Q here is the reduced order state, again, whose dynamics can be obtained from the full order structural dynamics using the Galerkin's method. So the reduced order model is shown at the bottom of this slide. And this figure provides an illustration of how the POD modes in this application example look like. You can see that each POD mode captures certain deformation patterns associated with this process. So one remark that I can make here is that only recently we realized that we could actually make this reduced order modeling even more accurate. So the idea is like this. So it is well known that the optimal POD basis is only locally optimal for the parameters used to generate the data. So in the context of our application, suppose that we're dealing with this high-dimensional collision problem. Given any collision scenario, we can generate some data using computer models, and based on the data, we can obtain the optimal POD basis. But obviously, this POD basis is only optimal for this collision scenario. If we change the collision scenario, naturally, we need to update the optimal POD basis. But we haven't done so in our current framework. So what we did was we merged data from different collision scenarios and find one global POD basis and apply that POD basis to all collision scenarios. What can be really helpful here is to establish a mapping between the parameters and POD basis. So if we have a model like that, so given any collision conditions, parameter settings of the PDE, we could use the model to generate the optimal new POD basis. It turns out this is completely possible. So in one of our very recent papers, we described a regression tree-based method for adapting reduced order model in the Grassmann manifold. What we believe here is that if such a seemingly simple regression tree method works well, so other more sophisticated advanced methods can provide us with even better results. But this is really new, so we have not yet incorporated this into our current modeling framework, but this is definitely something we would like to work in the next couple of months. So let's come back to the reduced order model that we have right now. So Q here is the reduced order state, and the second term here is the nonlinear internal force term, which is the troublemaker. And the term on the right side, that's the external force term. So, unfortunately, the evaluation of the second nonlinear internal force term still requires computing the original high-dimensional displacement vector U using computer models. The computation scales with the original high dimension rather than the reduced order dimension k. So we need to do something about this second term. Initially, what we thought was, how about we just replace it by a black box model, because we know the input and output of this nonlinear term, so we can totally train a data-driven model such as a neural network model, and then replace this nonlinear term by a black box model. In that case, we can actually compute the trajectory of the reduced order state iteratively. But our initial investigation quickly showed that this is unlikely to perform well if the problem is highly nonlinear, because it's not difficult to imagine that the prediction error associated with this Q and its derivatives at every single time step can quickly accumulate and are magnified. So as a result, the predicted trajectory can quickly deviate away from the actual trajectory obtained from finite element analysis. So we need to do something else. Since we're not able to learn it, so our current solution is to bypass it by directly establishing the relationship between the external force on the right side and the reduced order state on the left side, because both of them are vectors of functions which look like this in this particular application example. So the figure on the left side shows the profiles of the reduced order state over time for different POD modes for the 35 impact conditions. And the figure on the right side shows the profile of the reduced order external force for different POD modes over time for the 35 impact conditions. Looks like all we need to do is to establish the mapping between these profiles. Again, this is possible. For example, we could use the multivariate functional principal component analysis to represent the reduced order profile by a very short vector, psi q, which does not even depend on time. So similarly, we can use multivariate functional PCA to represent the external force profile by another short vector, psi f, which does not depend on time. And then what we need to do is to establish the mapping between these two short vectors through a linear model, for example. It doesn't have to be linear, but it works pretty well in this particular application. And also, we can show that it is basically a multivariate function-to-function regression model from the external force profile to the reduced order state profile. So if we can do this, now we're ready to address the prediction problem at any impact condition parameterized by P star. So the first step is to predict psi f from P star, and because psi f determines the reduced order external force profile. In our research, we used multivariate Gaussian process to achieve this goal, which is pretty standard. And from psi f, we can obtain psi q through the function-to-function regression, and then through the multivariate functional principal component analysis, we can recover the trajectory of the reduced order state. And finally, through POD, we're able to predict the aircraft surface deformation at every single location in our model. So we can not only obtain the point prediction, we can also systematically quantify the uncertainty propagation throughout the multiple stages of this process. So to show some numerical results, recall that we have data from 35 impact conditions. So what I'm going to do here is that I'm going to hold the data from the 35th impact condition. We're going to train the model using data collected from the first 34 conditions so that we can do a quick cross-validation. This animation, the bigger one, shows the predicted surface deformation process at the 35th impact condition. And the smaller animation shows the actual surface deformation process simulated from high-fidelity FEA. They will never be exactly the same, but we can see the potential of using this statistical modeling framework to capture such a nonlinear and dynamic process. And this figure shows the final moment aircraft surface deformation along the x and y and z directions, because this is the three-dimensional problem. So the first line shows the predicted surface, and the second line shows the actual, and the third line is the standard deviation. Again, we can see that this looks like the statistical model works pretty well. And we can actually take a closer look at the predicted aircraft surface deformation at three special locations. The first location, 1720, this is a location that is located within the collision center. So where the collision happens within the first 2 milliseconds. And the second location, 1799, this location is slightly far away from the collision center, and the collision happens after 2 milliseconds. And the third location, 1667, this is the location that is far away from the collision area. So where the deformation there is primarily due to the propagated stress wave. And the figure on the right side shows the predicted aircraft surface deformation at these 3 locations along the X and Y and Z directions, 3 rows. And in particular, you can see the red curves are the predicted, and the blue curve, that's the deformation process obtained from finite element analysis. You can see that at location 1667 and 1799, the model performs exceptionally well because the red curves match very well with the blue curves. And we can also see that it looks like it's harder for us to make accurate predictions at this location, 1720, because this is where the collision happens. If you look at the blue line goes up and down, because that corresponds to the a more violent vibration of the aircraft surface right after the collision, so making it difficult for us to accurately capture such a dynamic process. But this also shows what we need to do next if we want to further improve the accuracy performance of this modeling approach. Once we have data from these 35 conditions, we can always do a leave one out cross-validation. We try different ranks of the PUD basis. So if you just focus on the blue line, when the rank of the PUD basis is chosen to be 30, on average, we can achieve a 13% prediction error, out of sample prediction error. In terms of computational time, the statistical model takes about an hour and a half, but including training and prediction, of course. And running like one run of FEA simulation takes about 28 hours. So if you think about it, once we have the statistical model, we don't have to train it over and over again. And like many other data-driven approaches, the prediction step is actually very fast. It takes about slightly more than a minute. So that's already like 1,000 times faster than running this high-fidelity FEA. And of course, the price that we pay is this 13% prediction error. And now we're working to see if we can further reduce that prediction error. But that's the trade-off that we have to make for this type of applications, because our goal is not to replace FEA. Our goal is to make our work more efficient. And also, it's worth mentioning that we developed this framework based on a very generic and representative form of governing equations of nonlinear dynamical systems that can be widely found from a spectrum of scientific engineering applications. That means we can apply this method, of course, after necessary modifications to many other applications. For example, in one of our papers, we apply this methodology to model the heat profile during the manufacturing process. We can apply this methodology to monitor the vibration of wind turbines under different wind conditions in real time for condition monitoring problems. So this really shows the great potential and broad impacts of leveraging domain-aware statistics learning for a potentially wide class of engineering problems that traditionally rely on computationally expensive numerical models. We still see this as our preliminary work because we believe there are lots of exciting problems to be addressed along this direction. And some of the details are provided in this paper, and we presented this paper at the Informs conference a couple of months ago. So this literally brings me to the last few slides that I've prepared for today's seminar. Before I can conclude, I would love to share with you a roadmap that summarizes my past and my future research. My research experiences really started with using probability models and data-driven approaches to solve those reliability engineering problems. I'm still working in that area. And later on, my experience with IBM ushered me into a new area of environment and smarter cities, which eventually brought me into the area of domain-aware statistical learning. And also precisely because of my background and experience in reliability in smarter cities, that equipped with me the passion, the interest, and the capability to address those problems arising from urban resilience, energy, and sustainability. So in my presentation, I've talked about some of these applications and some of my future plans. So now I would like to conclude this seminar by showing you a little bit more about one of our recently started NSF-funded research projects in the area of urban sustainability. So the title of this project is International Networks Towards Future U.S. Urban Resilience. This is a multi-institution research project funded by the Office of International Science Engineering of NSF. So I serve as the PI of this project together with my dear co-PIs from 3 other schools. And the overall goal of this research is to establish an international research network to address those emergent issues in the area of urban resilience. So our current main international collaborators are the Singapore ETH Zurich Center on Urban System of Resilience and the United Nations Habitat Programs. And of course, we're working with multiple domestic NSF-funded centers, U.S. stakeholders such as national labs and industries, and other centers hosted from in the participating schools. And of course, right now it is just phase 1 plan. We try to expand this network significantly in the next couple of years. And leveraging this platform, the research activities will focus on 3 major aspects of urban resilience, including infrastructure resilience. This is related to what I used to do. And social resilience. I'm not in the area, but we have a co-PI in the area. And climate change of urban resilience. For example, the wildfire-related research fits nicely within this framework. So this is really a multidisciplinary research that definitely requires cross-disciplinary efforts and collaboration. So we really hope this platform can provide collaboration opportunities for people from different areas, including but not limited to system informatics, data science, of course, resilience, logistics, and sociology, and so on. So the long-term goal here is to spend another 2 to 3 years, potentially with continuing support from NSF, because we're going to compete for the phase 2 after 1 or 2 years, to grow this network, to make it a center that facilitates cross-disciplinary research and education. So of course, I hope I can achieve my goal and complete these tasks here with the University of Wisconsin-Madison, and I definitely need the help, and I appreciate the support from the best students, collaborators, colleagues, friends, and mentors that I could possibly find from this country, and that's why I'm here today. I appreciate this opportunity. So thank you for coming to my seminar. Thank you.
Questions?
Thank you very much. That was super interesting. And it's not really my area, so forgive me if this is a naive question, but it's a technical question. It was on the second part of your talk when you were talking about the kind of the reduced order model to try to more quickly predict the impact. So I think at one point you said we were going to have just one basis, one orthogonal basis, regardless of the impact conditions. Is that so I guess that can't always work for any sort of physical process, probably. But do you have, why is this a good idea in this case, or under what conditions will you be able to sort of do this aggregation or averaging, maybe?
Yeah. Okay, that's a good question. So we have thought about this a couple of times. So right now, what we're doing is that we have one global basis for all conditions. So this works if we make the rank of the PUD basis large enough so it can capture all this, minor deformation patterns. So, but to us, it's not the optimal way for doing this. So that's why we're working on this paper. Basically, it will enable us to establish the mapping between different collision conditions and the PUD basis.
Okay.
Yeah. So people from applied math area, so they use Lagrangian interpolation in the Grassmann manifold. But we believe if that works, we can introduce these data-driven models, including Gaussian process. Currently, we're working on the wrapped Gaussian process on the Grassmann manifold. We need to consider the geometry of it to solve this problem. So the challenge here is that we cannot do the interpolation of 2 PUD basis matrix in a linear space. Because if we take the average of 2 PUD bases, we're not going to get another proper basis. So we have to look at the subspaces spanned by these two POD bases, which belong to the Grassmann manifold. And then we can define the remaining distance on the Grassmann manifold and use that distance as the distance matrix between two POD bases matrix. So that builds the foundation for the regression tree-based method and Gaussian process method that we're working on right now. Yes?
Very interesting.
Thank you.
Any other questions?
So in your first work, like when you build up 3 different type of models for dynamic system, so it's a data-free method, or you need data to fit the statistical model?
We need data, yeah.
Okay.
Okay, so for the work with Singapore, so they provide the data. I don't have access to their data, not anymore. But for my work for wildfire problems, we have all the data that we need because those data sets come from NOAA, NASA, from the public domain. So we don't have any data issue there. So the only data issue that we can foresee is the solar energy production data. So we don't have the data from individual sites. We only have the production data from aggregated areas. For example, if we go to the website of CAISO, California, so we can actually see the total amount of solar energy production data from 3 different areas, updated every 5 minutes. So we're going to start from there. If we have a collaborator, in fact, if we're willing to pay the money so we can get the data, we can buy the data from individual sites. But environmental data, atmospheric data, they're freely available from NOAA and NASA. So
one critical challenge to apply the physics like a PDE model to do prediction, etc., is there are a lot of parameters we don't know the value, right?
Yeah.
In those different equations, we have a lot of parameters, but those parameters we cannot observe or we don't know. So that's why in the research areas, a lot of this model calibration work.
Yes.
Like based on the data we observed, we try to inversely compute what's the good parameters for those PDE equation. So your work try to build up equivalent statistical work, like you introduced the first work.
Mm-hmm.
So what's the relationship between your work with those model
calibration
work?
Okay.
Can your work be used for model calibration?
In a broad sense, yes. But the key difference here is that if we do model calibration, that's still 2 separate processes. We run the physics model first, and then we calibrate it using observations. But here, we have a single integrated process. We're not running the physical process. We use the physical equation to determine the parametric structure of our data-driven approach. And then we use data, back to your first question, to estimate those unknown parameters. So essentially, what we have here is still a statistical model motivated by governing equations. Yeah, that's the key difference.
So you are saying when you use physics PDE equation, you don't need to know the parameters for this physical phenomena. You just bring in those unknown parameters into your statistical model. Then you use data to estimate those unknown parameters. But in that case, will you make the problem more complicated? So, you are saying you did a transformation of the original unknown parameter into a statistical model. Then you use data to estimate it.
Yeah.
Or can we directly use the model calibration to calibrate those parameters based on the physics PDE?
Yes, that's a good question. So we don't need the parameters or the output from the physical model. We just need the structure to determine the structure of the data-driven model. In terms of which model is more complicated, I would say the statistical model has a simpler form in general. The only complexity that I can see here is the computation. Because we develop the statistical models for real-time prediction to support real-time operations. So they need to be simple enough and fast enough. Like for example, in a wildfire application, we need to update the results every 5 minutes because we have 5-minute resolution data from NOAA satellite data. So I cannot say the statistical model is simpler, but in terms of the parameter estimation update, that can be challenging, actually very challenging if we want to update those parameters over time. But in terms of the physics-based models, I think computation is also a problem. So that prevents us from using those models to do real-time predictions. I see these two models in two different domains. If I want to answer long-term or mid-term prediction questions, I would rely on physics-based models. If we want to do this short-term predictions to make real-time decisions, I would use those statistical models, but hopefully they're well justified from physics. So I think the application domain may overlap a little bit, but I want to see them. These are two different application areas. Okay. Yes?
Okay.
So in the first study, you mentioned both that when you had the comparative models, that your model improved in terms of the overall error, but then also improved in terms of interpretability. And I'm curious if you had any kind of specific metrics around interpretability, or just kind of it's just inherent in the modeling framework.
Okay, that's a good question. In that particular comparison, we didn't have the metric for interpretability because I made that conclusion because if you look at the model construction process, okay, so let me show you these two models because it's very clear that the other two models are pure data-driven approaches. For example, this model, LGK 2018, that's actually my paper. So we use spatial temporal auto-regressive process to make predictions. There's no physics at all. And the second co-track method, so this is an image-based analysis that basically compare two radar images and try to figure out the wind vectors. So again, it's a pure data-driven approach. There is no PDE behind this, no physics behind these two approaches whatsoever. Yeah. So from that perspective, I can say that it seems like our approach is more interpretable compared to these approaches. But if I present this to atmospheric scientists, they might think my approach is pure data-driven and their approach is more physics-driven. So yes, it's in a relative sense.
Okay, I think we ran out of time. Let's thanks for our speaker again for this intriguing talk.